Welcome back. Today we're going to be looking at rational functions, kind of veering off of this polynomial trail for a little bit as we look at graphing rational functions, how to find all the features of them, including vertical, horizontal asymptotes, zeros, y-intercepts, x-intercepts, all the things you can need to know about rational functions. So let's go ahead and get started. This section will be a little bit longer, so hopefully we can get through it fast, but I would highly encourage you to read through the textbook, as we won't get to do every triad on this section because it's just got a lot of them. But when we get to the very last triad 8 on this page, we'll see that we can kind of lump everything into one problem, where you can do all of the things we learn in one problem, and that hopefully will be a pretty good review. So let's go ahead and get started. The first thing we want to point out is you've already looked at a rational function, so you should know a few of the features. You know that the toolkit rational function has a vertical asymptote right there at x equals 0, and a horizontal asymptote also at y equals 0. And then the end behavior you can look at and look to the end behavior the same way we looked at end behavior of every other function. So what we're going to do is they've given us the end behavior for the toolkit rational function right here. We are going to give them the end behavior for the toolkit rational squared function. So it says find the end behavior and local behavior for the reciprocal squared function. Reciprocal meaning flip, like a rational, and squared meaning squared. So that's f of x equals 1 over x squared. And if you remember back to when we memorized toolkit functions way back on the first day of class, maybe this first day of functions, it looked kind of like a volcano. That's going to be really important to remember as we go to graph really way more complex ones, is that the squared feature, or the 2 right there, made the asymptote look kind of like a volcano, whether up or down. And the single, or the single exponent, the 1 as an exponent, made it split. See how it like split, one side going up and one side going down? That's a pretty important feature to point out while we're here. All right, so we've got this. Now let's find out what that end behavior and local behavior is. So as x goes that way forever, as x approaches negative infinity, y doesn't seem to be going bigger or smaller. It seems to be getting super duper close to 0. And that's okay. It's okay to have a horizontal asymptote where y approaches a number and not infinity or negative infinity. And likewise, as x gets super big or goes to infinity, y also goes to 0. Now it's going to 0 from the top side, but that's okay. We don't have to note that. We're just telling you that it goes to 0. This is going to be the same asymptotes as up above, if you notice that. That horizontal asymptote is the same. What's going to be different, however, though, is when it approaches it from the left and the right side. So the way that we denote this, I'm going to move this up so you can see what it goes with and where we got it from. This end behavior goes with that. This end behavior goes with that. Change colors here, and we're going to go as x approaches 0 from the minus side. I'm going to put it on the left side so you know that we're looking at this one right here. As x approaches 0 from the minus side, on the left side, on the minus side of 0, y approaches infinity. Y goes up forever and ever and ever. And then one last color, as x approaches 0 from the plus side, y approaches infinity. And that is how we define end behavior. You use the exact same strategies to define it for any function. This is just one of the toolkits. Awesome. Let's keep going. We are going to sketch a graph looking at those 2 asymptotes that we've already been looking at, but shifting them. And we're going to talk about how when we graph a rational function, we start at the asymptotes and shift those and then worry about the function instead of plugging and chugging numbers. So, important thing to realize is find the horizontal and vertical asymptotes for reciprocal squared. We're working with the same volcano-looking function, so we know the function normally looks like this. Say that's f of x equals 1 over x squared. Totally fine, but we're not looking at 1 over x squared. We're looking for a shift. And so we know normally that has a horizontal or a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. But right here it's saying it's shifted to the right 3. So we're just going to take that asymptote and shift it over 3. And then we're going to take that horizontal asymptote and shift it down 4. So it used to be on the XY grid, and now it's on this new red and blue grid for the center point or the middle point of our function, the axis of symmetry and the horizontal asymptote. And now we just graph our volcano-like function as best as we can. Whoops. We graph our volcano-like function, usually plotting those 2 points. If there's no vertical shift, I always plot the 1 and the 1 first, or the 1 away point, those two. Or if it were the normal function or the non-squared function, you'd plot down here. And then drawing our shape. Oop. Whoops. Messing up all sorts of lines. Here we go. Looking like a volcano because it's squared. Awesome. So the shifts happen at the asymptotes, and then you draw your function from there. I'm going to skip through triad 3 so that we can jump to this domain. Really, we're trying to get to triad 8 so we can see all of these things applied into one. So let's do triad 4 where it says find the domain. Nothing's changed. You already know how to find domain. Remember, there's 2 things to look for when you look for domain. You can look for a number over 0, or you can look for a negative number in the square root. Those are both bad. Right here, do we have a square root? No. So we're just looking at a number over 0. We're going to take this and derive the fact that x better not ever be, x cannot equal 1. And we're going to take this one and derive the fact that x cannot equal 5. And using those 2 facts, we know our domain. We know that x is technically allowed to be every number in the world except for 1. Then we're going to go from 1 to 5. Then we're going to go, unite it with. Then we're going to go from 5 to infinity. On a number line, what that looks like is you got open circles at 1, open circle at 5, and every other number in the world is allowed to be on your graph. Now, what are those holes are, we don't know yet. We don't know if they're vertical asymptotes or removable discontinuities. We don't know if they're volcano horizontal asymptotes or opposite side vertical asymptotes. We just know that there's something missing there in the domain. We're not allowed to have those 2 numbers. All right, now we're going to find out, well, how do we know what happens there? What's interesting that's happening there? And so for that, we are going to have to factor. We have to factor the top, we have to factor the bottom, and look for those holes again. So here we have a definition of removable discontinuity, but we're going to talk about vertical asymptotes in the same step, because if you don't have a removable hole, you've got a vertical asymptote. And we'll even talk about how to define what type of vertical asymptote. And so if you factor the top using that perfect square, you know we've got x plus 5 and x minus 5. And then the bottom, ooh, that's a little tougher factor. I'm going to do it in steps. I'm going to factor out an x first. So I've got an x outside. And then if I factor out an x, we end up with x times x squared minus 6x plus 5. Is that a nice, neat factor? Negative 5 and negative 1 seems to make it 1. So we have x minus 5 and x minus 1. And so you'll notice we have 3 domain restrictions. We have x cannot be 0 from the first term, x cannot be 5 from the second term, and x cannot be 1. Now that's true, but let's find out what type each of these is. So because one of those factors can eliminate itself, or one of those factors factors out, you still can't let x be 5, but the function, that's not going to affect what the function looks like. And so at this, when they cancel out like that, or when you turn into 1 on top of each other, that x equals 5 is known as a removable hole, or a removable discontinuity. What that looks like on our function is just some squiggly line, and then when we get to 5, there's a hole and it just keeps going. So that would be at 5. I don't know exactly what this function looks like, but that's what a removable hole looks like. Probably this function looks a little more like this. Maybe you got a vertical asymptote, maybe you got this, I don't know. But you got a removable hole at 5, wherever 5 is. All right, let's keep going. We could say, well, since the other 2 don't cancel out, or the other 2 don't have factors that match on the top, they're both vertical asymptotes. And then we could even take it a step further, and we can look at the multiplicity. Even though it's on the bottom, it's not technically a multiplicity, but we can look at the exponent associated with each of those factors, and we could say this vertical asymptote is either going to look like this or like this. We don't know exactly which one it is, but we know it's going to split. We know it's going to be split at the vertical asymptote, whereas if it were squared, it would look more like a volcano where they go in the same direction. All right, let's keep going. Oh, hang on. We didn't actually answer our question. Sorry, sometimes I get ahead of myself. We need to answer the question well and say, oh, well, let's define the vertical asymptote. So x equals 0 and x equals 1 are our vertical asymptotes. And our removable discontinuity, it occurs at x equals 5. Cool? All right, let's keep going. Horizontal asymptotes. This is a fun one. Horizontal asymptotes has a little extra step, a new algorithm that we have to look through. It asks us for vertical though, so as a little review, let's go ahead and find vertical asymptotes. Does anything cancel out? Nope, all those are different. And so we know our two vertical asymptotes are x equals 2 and x equals negative 3. Remember, those are going to be straight up and down lines where it looks something like this. We don't know exactly what it looks like, but we know there's a vertical asymptote that splits at 2 and negative 3. Now for horizontal asymptotes, we have an algorithm that we have to look at. We have to look at the leading terms of both polynomials, the top and the bottom. So we need to look at not just of one factor, but of the whole term. And so if we were to go to FOIL these and look at the leading terms, I'll write it out. Leading terms. If you were to multiply the first two, the leading term would look like 4, because 2 times 2 is 4, x squared, dot, dot, dot. We only need the leading term, so we don't have to FOIL the whole thing for horizontal asymptotes, though when we get to triadate and we sum this all together, we're going to factor the whole thing. Over x times x is x squared. All right, and now we have 3 options that we have to pick between. We have top exponent bigger, bottom exponent bigger, or same exponent. And these 3 are defined up above at those bullet points right there, where the degree of the numerator is less than, greater than, or equal to. I'm going to do it down here so we can see it happen. If the top exponent's bigger, then we've got no asymptote or a slant asymptote, which means the asymptote is slanted on a linear function. So kind of like if you had a linear function, it would look kind of like zoom, zoom, and we'd have a asymptote on a linear function. That's a special case that only occurs when it's exactly 1 over, when the degree of the top is exactly 1 over the degree of the bottom. And we don't see that very much, so I'm going to write x is n and x is n minus 1. That would be the slant case. No asymptote is when it goes to infinity and it's just going on forever. Like you look at a parabola, parabolas go on forever upwards. Bottom exponent bigger, you've got your asymptote at x equals 0. It's probably the easiest one to recognize. If the bottom's bigger, it goes to 0. That's like the case of 1 over x or 1 over x squared. Your exponent's bigger, so your asymptote's at 0. And then if you have the same, you take the a over b that are your leading terms, or your leading coefficients. Leading coefficients. And so if we look at this one that we're working on right now, we see that the exponents are exactly the same. And so all we're going to take is our leading coefficients and say our horizontal asymptote is 4 over 1. So x equals 4 over 1, or x equals 4 is our horizontal asymptote. So we've got our VAs of 2 and negative 3, and we've got our HA of 4. Not 4, of y equals 4. Oh, hop down there, change that x to a y. X, that was Hoy-Vuck's mistake, where horizontal lines are in the form y equals and vertical lines are in the form x equals. And so your horizontal asymptote is of the form y equals. All right, I'm going to skip through intercepts for the sake of time to keep this video short enough, but I will show you how. The way you find an intercept is the way you find an x-intercept. It's exactly like we've done before. You set the top equal to 0. That's an x-intercept. The way you find a y-intercept is exactly like before. Y-intercept, you set x equal to 0, or you find f of 0, and you just plug it in. So I'll let you practice that, try that on your own. We will do that on our last problem, but I want to go ahead and hop down to it. And so we are going to get to graphing a rational function here, this triad 8, which we're going to do everything. We're going to do the x-intercepts, the y-intercepts, we're going to do the asymptotes, we're going to define the behavior at the asymptotes, we are going to solve for any removable discontinuities. We're going to do everything all at once. And so here we go, we're going to start. We'll follow their instructions where they say start with the y-intercept because it's probably the easiest. So if we start with the y-intercept, that is just finding f of 0. So we plug it into the top and we get 2 squared. We get -2. We get a 2 on the outside. We get -1 squared. And we get -3. So that would be 4 times -2 is -8 over, that's a 1, so 2 times -3 is -6, and we get 4 over 3. So our y-intercept is 0, 4 over 3. So we're a little bit above 1. So maybe right there. Keep these in different colors. We did the first step. We found our y-intercept. Second step they ask us to do, factor out the numerator and the denominator. Look right here, they've done that for us. Fully factored form. We don't really have to do anything else. If they gave you long polynomials, you'd have to factor them on your own. So check mark, we're done with step 2. For factors in not common, we need to determine where the x-intercepts are. And so look right here. Does anything cancel out? Nope, those are all the same. And so our x-intercepts are going to come straight out of the top. And since it's already factored, they're kind of nice and neat to find. Your x-intercepts come just like they would in any normal function. -2, 0 from the first term, and 2, 0 from the second term. That comes from setting the top equal to 0. Important to note that if something would have canceled out, we wouldn't label it an x-intercept, we would label it a removable hole or removable discontinuity. Because we didn't cancel anything out, they're both x-intercepts. So let's go ahead and plot those. We got an x-intercept here at 2, and here at -2 and 2. And now we can keep going. We got ourselves our x-intercepts. Next step it says to find is find the multiplicities of those x-intercepts to find local behavior. So at the -2, we have a even, and even means bounce or touch. And at x equals 2, we have odd, which means cross. Now I don't know exactly which way they're going to cross, like this or this, or bounce like this or bounce like that, so we're going to have to wait and see. But if we want to go ahead and label them, we totally can. We can say this one's going to bounce off of the x-axis, and this one's going to cross the x-axis, because this one has a multiplicity of 2, and this one had a multiplicity of 1, based on the exponent of the factor. All right, so we found our multiplicities, good to go. Now we need to find the multiplicities of the factors in the bottom to determine the local behavior. And so we're going to look at our, we haven't found our vertical asymptotes yet. Okay, well, let's find our vertical asymptotes now. And do that in green. Vertical asymptotes. Before finding the multiplicity, probably a good idea to find those vertical asymptotes. So we look at the bottom and we set the bottom equal to 0, remembering removable discontinuities are ones that cancel. We don't have one in this example, but it's important to remember. So if we set the bottom equal to 0, we see that our first vertical asymptote is at 1, and our second one is at -3. That just comes from setting each of those terms equal to 0, and we can look at the behavior at each one. Look at the behavior of that one, it's either going to go up like a volcano or down like a trench. And if we look at that -3, it's going to split. We don't know which way it's going to split. We'll find that out later. All right. There's our vertical asymptotes. Let's go ahead and draw them on the graph. We've got a vertical asymptote at +1, and we've got a vertical asymptote at negative, that should be a +3. All right. Now here we go. We're going to keep going through these steps, and we're going to find the horizontal asymptote. So I'll do this in black, HA. We are going to have to look at the leading term. So if we've got x squared and x on the top is going to be x cubed. Top leading term, bottom leading term, 2 times x times x times x. So we're going to have 2x3. Now because our exponents are exactly the same exponents, we're just going to take the ratio of the leading coefficients and say our horizontal asymptote is at 1/2. More explicitly, y equals 1/2. So we'll zoom in pretty big and we'll draw a horizontal line at 1/2. Now we're getting a feel for this graph. All right, after this, if you need to plot any more points to graph your function, you can, but we probably have enough information to do it. So for instance, one of the most important things to think about is your x-intercepts, because you can't touch the x-axis ever again. You are not allowed to touch the x-axis because we've already calculated our x-intercepts, and so this red to blue dot right here has to connect to each other. There's no possible way for it to go down and back up because you would have had to cross the line, so they have to go and hit each other, which means it's going to go up right here. And then using the behavior of that asymptote, so look at this x equals 1, we know they go the same direction, so we can draw another little arrow up there and say because it's got to look like a volcano or a trench and we went up there, we're coming down here. And then using our behavior of the intercept, so this is a lot, I know it gets a lot, but you got to bring all of these things back in together. Our behavior of that intercept, I'm going to go over and look. The x-intercept at 2, it crosses. It's going to have to cross and go all the way down. Now once again, we can use the behavior of that asymptote at 3 to say, oh, they have to split because they had a single multiplicity. And so we're going to start up at the top and work our way down to that horizontal asymptote. So you can see the behaviors of the asymptotes and the behaviors of the dots, or the x-intercepts, gave us everything we needed to know without having to plug in another point. And last but not least, we have behavior here at this dot, or this x-intercept. The behavior at the x-intercept -2 has to bounce. Makes a lot of sense because we got to get back to that horizontal asymptote. So we're going to bounce off the axis and approach that asymptote forever. And here we have that function f of x graphed. It says to describe behavior, so maybe we'll go ahead and do that real quick. It's going to have a lot of descriptions, but that's okay. We'll start at the far right, and we'll say as x approaches -infinity, y approaches, what was that horizontal asymptote? 1/2. Now we can go to the other one and do the same thing. As x approaches infinity, y approaches 1/2 again. Now we can go to this spot and say as x approaches 1 from the negative side, y approaches infinity. And as x approaches 1 from the positive side, y approaches infinity still. And that's come from up there. Change our color one last time. I'm going to trace over this in an orange asymptote so we know where we're coming from. We're going to look at those two behaviors and say as x approaches, what was our last vertical asymptote? 3 up there. As x approaches 3 from the negative side, right here, y approaches -infinity. And as x approaches 3 from the positive side, because the multiplicity was odd and we had to split, y approaches +infinity. And there we have all of our behaviors of that triadate and a good function of that graph, where we didn't have to plot a single point. We just used the properties of rational functions to graph and find all behaviors. Thank you for watching this far. If you need to go and practice some of these graphing rational functions, I would highly encourage looking through the exercises in the book before starting your homework. And I will see you next time.